All right. Hello, everyone. Welcome to lesson 23 of MAC 2311, Calculus 1. Today, we're going to be learning something called Lhopitals Rule. It's a French person's name. It has the little, I actually don't know what they call that. I'm going to stop. Anyways, um, what L'Hopital's rule enables us to do is it enables us to find limits that we couldn't have otherwise done before. Like, for example, let's say we wanted to do the limit as x goes to 0 of sine of x minus x over x squared. So no matter how hard we try, we can't use any algebraic tricks to really break this down at all. So we're forced to try something else instead. And another limit that we wouldn't quite know how to do right now is the limit as x goes to infinity of ln of x squared over root x. Seems like the top and bottom here are both getting larger and larger, so what's going to happen in the long run? And here it seems like the top and bottom are getting closer and closer to 0, but it's unclear what's going to happen because 0 over 0 isn't defined. All right, so what we're going to do is we're going to define a special rule called L'Hopital's rule. By the way, you may also see it without the little thing over the O, but with an S written in there as well. All right, so what is this rule? So suppose we have F and G, and we want these to be differentiable functions, and we want G of X to not equal 0 near a point X equals A. Although it could equal 0 at A, it just can't be 0 near A. Okay, then what do we have now? So if either of the following things are true, the limit as x goes to a of f of x equals 0, and the limit as x goes to a of g of x also equals 0. So that's one situation. Or the limits instead both go to some sort of infinity. And it could be positive or negative infinity, and it doesn't have to be the same one for f and g. So f could go to positive infinity, g can go to negative infinity. It doesn't really matter. Now, if one of these two scenarios is true, and we can't mix and match them, they both have to be 0 or both going to infinity. And one more condition on top of this, the limit as x goes to a of f prime of x over g prime of x exists, then the limit as x goes to a of f of x over g of x is the limit as x goes to a of f prime of x over g prime of x. So what we're essentially doing is we're replacing the limit of the quotient of these two functions with the quotient of their derivatives instead. And one way to kind of imagine L'Hopital's rule is you can sort of imagine it as a tiebreaker. Like, so for example, up here, natural log goes to infinity, even more so if it's squared, and so does root x. But which one ends up going to infinity more quickly? And the rate of change of each of these functions is represented by f and g prime. So we see what happens as those rates of change go to infinity. So you can almost imagine L'Hopital's rule as a sort of tiebreaker. All right. Now, L'Hopital's rule specifically lists 0 over 0, if we have this condition, or infinity over infinity as cases where we can use L'Hopital's rule. But it turns out that there are actually 7 different situations, not just 2, where we could use L'Hopital's rule. And these 7 situations are called the indeterminate forms. All right, so let's take a look at what these are. So the first two are infinity over infinity and 0 over 0. And I put these in quotes because these quantities aren't defined. These aren't even numbers. What I mean by this is that the limit on the top is going to 0, and the limit, oh, whoops, I'm not here. The limit on the top is going to 0, and the limit on the bottom is going to 0, or they're both going to infinity. They don't actually have to equal that if you plug in the number, if you can. So we have infinity over infinity, 0 over 0, but it would also work for a limit that looked like 0 times infinity. So we have something going to 0 times something going to infinity. What's going to happen then? It works for infinity minus infinity, and then it works for the 3 exponential indeterminate forms. 1 to the infinity, infinity to the 0, and 0 to the 0. So these indeterminate forms, they more or less are where 2 rules of math are kind of coming head to head with each other. Like, for example, if you multiply anything times 0, it should be 0. But on the other hand, if you multiply something by infinity, it should go off to infinity. So what happens if you multiply those 2 together? Or, for example, let's say right here, usually infinity divided by anything will be infinity, but anything divided by infinity should be 0. So which way is it going to go there? And you can imagine similar scenarios with each of these right here. What's going to happen? Like, here's another one. 0 raised to anything is usually 0, but anything raised to the 0th power is usually 1. So which one is it going to be in that form? But we could use Lhopitals rule for all of these situations. So what I'm going to do is I'm going to do a few examples where we have at least one example of each one of these. Let's start off with the basic examples where we have one of the 2 forms where we could use Lhopitals rule right away. So let's take a look at those limits that we wrote earlier. So suppose we have the limit as x goes to 0 of sine of x minus x over x squared. Well, we see that the top is going to 0. We send both of these to 0, they'll be 0. And then the bottom is going to 0 as well. So this means that we're in this situation here, so we can use Lhopitals rule, meaning we can replace the top and bottom with their derivatives. And one thing I want to emphasize here, this is not a quotient rule, even though this was a quotient. This is the derivative of the top divided by the derivative of the bottom. All right, now one thing I like to do to kind of show my work for this is I put a little LR above the equal sign anytime I use Lhopitals rule. All right, so now I do the limit, so I do the derivative of the top. So I have cosine minus 1, this derivative. And then on the bottom, I end up getting 2x. All right, now hopefully after we do Lhopitals rule, our limit ends up getting better to do. It's something we can do. But if I plug in 0 now, I have cosine of 0, which is 1, minus 1, which is 0. And then on the bottom, I have 0 as well. So I still have an indeterminate form. But the fact of the matter is that we can actually use Lhopitals rule as many times as we'd like. So I'm going to use Lhopitals rule again. I'm going to do the derivative of the top here, which will just be negative sine of x. And then I'll do the derivative of the bottom, which will be 2. All right, now we see we're not going to use Lhopitals rule again because we have a 2 on the bottom, so we're not going to be able to get any of these. But the top, as x goes to 0, sine will go to 0. Overall, this limit ends up being 0. All right, so that's one instance of Lhopitals rule. Let's take a look at that other example where we have things going to infinity. So now if we want to evaluate that limit, let's go ahead and do so. So we see that the top and bottom are differentiable, and they're both heading to infinity, because log goes to infinity, and so does the square root. So let's go ahead and use Lhopitals rule to figure out what's going to happen. All right, now on the top, I'm going to need to use the chain rule. So I first differentiate the square function, I leave the natural log alone, and then I multiply by the derivative of natural log. Down here on the bottom, the derivative of square root of x is 1 over 2 root x. All right, so what's going to happen now is I'm going to have to simplify this. So this, a lot of times when things come out of Lhopitals rule, they end up pretty messy. So we want to reorganize it and see if we can make sense of it, and maybe we have to use L'Hopital's rule again. So I'm going to move the 1 over x down here. 2 ln of x, and then the x can move to the denominator, but we already have a fraction down here. So x over root x will simplify to root x, and 2 over 1/2 will be 4. So this will be 4 ln of x over the square root of x. All right, but once again, we have log and we have square root, so we're going to have to use L'Hopital's rule again. All right, the derivative is a bit easier this time, though. We do the derivative of natural log of x and get 4 over x. And we do the derivative of the bottom and get 1 over 2 root x. All right, now what I'm going to do is I'm going to multiply the top and bottom by 2 root x. So multiplying the bottom by that has these cancel out. Multiplying the top by that will make this be 8 root x over x. Now you might think, okay, well, we're going to do L'Hopital's rule again because both these go to infinity, but we could rewrite this as 8 over the square root of x. And now as x goes to infinity, this is going to infinity, but this will remain as 8. So as our denominator gets larger and larger without end, we end up with 0 as our limit. Now it's just a coincidence that both of these are 0. We won't always get 0 out of L'Hopital's. All right, let's move on to another example. Let's take a look at the limit as x goes to pi of sine of x over x. All right, so your first guess might be to go ahead and use L'Hopital's rule, and then we'll be looking at the limit of cosine of x over 1. But before we do that, we need to check if it's one of the indeterminate forms. So if I plug in pi into here, I do get sine of pi, which is 0 up here. But on the other hand, I just get pi down here. So this isn't an indeterminate form at all. This will just be sine of pi over pi, or 0 over pi, 0. So my warning to you is that now that we know L'Hopital's rule, we're tempted to use it on any quotient of functions we're taking a limit of. But that doesn't mean that we can use L'Hopital's rule in those instances. In fact, even if we could use L'Hopital's rule, it was easier to just plug in the number in this case. So watch out. Don't try to use it on everything. Make sure you can actually use it. All right, so we've covered the infinity over infinity and 0 over 0 indeterminate forms. Let's move on to an example where we have 0 times infinity. So a typical example of this would be the limit as x goes to 0 from the right of x times ln of x. This is a limit that is fairly common when we have to do limits. So if we plug in 0 right away, we have 0 here. And then as the inside of a log goes to 0, the log goes to negative infinity. So this is going to be a 0 times infinity indeterminate form. Now, before we take any derivatives, we don't have this in the form where we could use L'Hopital's rule, because L'Hopital's rule requires us to have a quotient where both are going to 0, both going to infinity. But we don't even have a quotient at all. Now, what we can do is we can make a quotient by moving the x to the denominator. So log will stay where it is, and this is technically x to the 1, right? So if we move it to the denominator, its sign multiplies by -1, and we have x to the -1. Or another way of writing this, oops, these are from the right, would be 1 over x. All right, now why did I do this? I feel like I just made it look uglier. Well, if I plug in 0, the top is going to negative infinity, and the bottom is going to, in this case, positive infinity. So now we do actually have a case where we could use L'Hopital's rule. So for 0 times infinity, move something to the bottom. And you should be able to use L'Hopital's rule in that instance. All right, so let's go ahead and use Lhopitals rule here. So we have the limit as x goes to 0 from the right. The derivative of the top is 1 over x, and the derivative of the bottom is -1 over x squared. All right, now I'm going to multiply the top and bottom by x squared to simplify. And then we end up with the limit as x goes to 0 from the right. Now on the bottom, these will cancel. And we still have that negative though. And the top, we have x squared over x, which is just x. Overall, we're going to get -x, which is we send x to 0 here, we get 0. I assure you, it's actually a coincidence that all of these are 0. I don't think they'll all end up being 0. Hopefully they won't, but it's a coincidence that all these are 0 so far. But anyways, that's how we handle a 0 times infinity case. Next, let's take a look at infinity minus infinity. So an example of this might be the limit as x goes to 0 from the right of cotangent of x minus cosecant of x. All right, now why is this infinity over infinity? Well, cotangent is cosine over sine, and cosecant is 1 over sine. So for both of these, as x goes to 0, sine will go to 0, meaning that we're dividing by something getting close to 0, meaning we're going off to infinity. That's why this is an infinity minus infinity case. All right, now how do we deal with this? The way we deal with an infinity minus infinity case is we combine things into a single fraction. So we can write it like this. So we write cotangent like this, cosecant like this, and then they have a common denominator. So you have the limit as x goes to 0 from the right of cosine minus 1 over sine of x. All right, so now we're in an instance where we could use Lhopitals rule, because as you can see, the top is going to 0, because we have 1 minus 1, and the bottom is going to 0. So this is 0 over 0. We can use Lhopitals rule. So we have the limit as x goes to 0 from the right. The derivative of the top is negative sine of x, and the derivative of the bottom is cosine of x. All right, now let's go ahead and plug in 0 and see what happens. If I plug in 0, I have 0 in the numerator, 1 in the denominator. So once again, we end up getting 0 for this. Wow, maybe I should have picked more diverse examples here. But anyways, so the moral of the story with infinity minus infinity, we need to combine fractions in some way. And we may not always have fractions, but what we want to do is we want to make a fraction and then combine it. And now the context for this will be different based on the different types of functions, but usually you want to try to combine fractions, or maybe if there are square roots, you multiply the top and bottom by a conjugate. Either way, you want to get it to the fractional form so we can use Lhopitals rule, where we have 0 over 0 or infinity over infinity. All right, the next example I know won't go to 0, so we'll have some diverse examples here. All right. Our next example is the limit as x goes to infinity of 1 plus 1 over x raised to the x power. Now, some of you may have actually seen this limit before, and you may already know what it's going to end up being. This is actually going to be the number e, so 2.71, et cetera, et cetera. So this limit here is often used as a definition for e. So this is where a lot of people consider the number e to come from. But what we could do is using Lhopitals rule, we can show that this limit will end up equaling e. All right. So this is going to be an indeterminate form 1 to the infinity. Now, this one may seem kind of strange. If you keep multiplying 1 by itself, no matter how many times you multiply it, it should still be 1. But we got to remember that these are things that are just approaching 1. Like for example, 1 plus 1 over x will never actually be 1. It'll always be a little bit bigger than 1. So we have numbers approaching 1 multiplied by themselves many times. So what we're effectively measuring here is we're measuring how quickly is this going to 1 versus how quickly this is getting big. So if this is getting big faster, our result will be large, but if this is going to 1 quickly, our result will be going to 1. All right, now the way we deal with this and the other 3 exponential indeterminate forms, this, infinity to the 0 and 0 to the 0, is we use exponentiation. Okay, so what's that? So we start with our limit here, and what I'm going to do is going to look kind of bizarre, but it's really going to help out in a minute. What I'm going to do is I'm going to rewrite this as e to the natural log of 1 over 1 plus x to the x. All right, now this looks pretty different, but remember these are actually the same thing because e raised to a natural log, these are inverse functions. So at any time we could cancel these out and end up back here. So this is a valid move right here. Now, why on earth do we do this? Well, the nice thing about natural log is that exponents in the argument of natural log can move out to be coefficients. So we have the limit as x goes to infinity of e to the x ln of 1 plus 1 over x. All right, so that's all well and good, but how am I going to deal with this e here? Well, the nice thing about e raised to a power is that e is a continuous function. So we can actually move the limit inside the exponent here. And remember, you could do that with any continuous function. So this also works for things like square or cube roots or trig functions or logs, but we're doing it with e in this case. Okay, now let's see what our limit looks like so far. So as x goes to infinity, obviously this will go to infinity. And as x goes to infinity here, we have a number heading to 0. That's going to be this. We have ln of 1 plus 0, which is ln of 1. ln of 1 is 0. So this is going to be an infinity times 0 situation. All right, so we need to figure that out. But if we go back a few problems, we already learned how to deal with that. We move something to the bottom. In this case, I'm going to move the x to the bottom. It usually pays to move the simplest thing to the bottom. So I have ln of 1 plus x, and then when x moves to the bottom, it becomes a 1 over x. All right, now if I reevaluate this, this is actually a 0 over 0 limit. And this is something that I could use Lhopitals rule. So when I use Lhopitals rule, let's see what happens. All right, the derivative of natural log of something is 1 over that something times the derivative of the inside. Now the derivative of 1 is 0, but the derivative of 1 over x is negative 1 over x squared. Okay, meanwhile, on the bottom, I do the derivative of the bottom, and I have negative 1 over x squared. Now that's actually rather convenient because this and that will cancel out right away. So I'm really left with the limit as x goes to infinity of 1 over 1 plus 1 over x. All right, now as x goes to infinity, this will go to 0. We have 1 plus 0 is 1, and then we have a 1 up here. So our limit ends up being e to the 1, or in other words, just e. So that's kind of a more detailed reason why this limit is equal to e. We can use Lhopitals rule to determine that when we use the fact that the derivative of ln is 1 over whatever's in here, and that e to the ln are inverse functions. All right, so we finally got an answer that isn't 0. You're not going to get 0 every single time for these Lhopitals rule problems. All right. So that was a 1 to the infinity example. Let's take a look at an infinity to the 0 example. Probably the simplest one of those is x raised to the 1 over x power. We're going to see what happens when our base gets very large, but our power gets very small. Now, the procedure for this problem and also the next problem will be very similar to what we just did up here. We're going to use e to the natural log to get it into a form where we could use Lhopitals rule. You have the limit as x goes to infinity of e to the ln of x 1 over x Now, because of the properties of natural log, 1 over x can move to the front. And I'm also going to include in this step moving the limit into the exponent. So this is 1 over x times ln of x, but I can imagine this another way. This is e to the limit as x goes to infinity of ln of x over x. All right, now this is rather nice because this is an infinity over infinity indeterminate form, meaning I could use Lhopitals rule. So using Lhopitals rule, I end up getting e to the limit as x goes to infinity of 1 over x divided by 1. All right, now obviously dividing by 1, we could ignore that. And then x going to infinity, well, this part's going to head to 0 because we're dividing by a larger and larger number. So e raised to the 0 is our answer, which ends up being 1. All right, so it turns out that this limit is going to end up being 1. So if we raise a larger and larger number to a smaller power, at least at these rates, we'll end up getting 1. All right, I'm going to do one final example here. This is an example of a 0 to the 0 limit, but as promised, this is going to be very similar to what we've just done. So this is going to be a very bizarre limit. We have the limit as x goes to 1 of natural log of x raised to the sine of x minus 1. All right, now if we try to plug in 1 right away, I should actually say 1 from the right because we don't want to have to worry about any negatives to an odd power here. So as we approach 1 from the right, this is going to 0 because ln of 1 is 0. And then this is also going to 0 because we'll have 0 in here and sine of 0 is 0. All right, now we're going to do this the same way that we've done the previous two examples. This method will work for any exponential indeterminate form. So this is the same as the limit as x goes to 1 from the right of e to the natural log of ln of x to the sine of x minus 1. All right. Now, because of log rules, this will move to the front, and I can also move my limit into e as usual. So I have the limit as x goes to 1 from the right, sine of x minus 1, and then I have natural log of x. All right, now let's take a look at this. As I send x to 1, I'm going to get sine of 0 here, which is 0. And as I send x to 1 here, I have something approaching 0 in here. But as the inside of this log heads to 0, the whole thing is going to go to negative infinity. So this is a 0 times, I guess, negative infinity in this case, limit. So we know how to deal with those. We move something to the bottom. All right, I'm going to move sine of x to the bottom. The limit as x goes to 1 from the right of natural log of x, and then 1 over sine of x minus 1. Now, there's a more compact way of writing sine of x minus 1, or 1 over that, excuse me. This is actually going to be cosecant of x minus 1. All right, now it's time to go ahead and use Lhopitals rule here. And why can we do that? Well, the bottom, so this is heading to 0, meaning that this whole fraction is going to infinity. And then we already saw that this is going to negative infinity. So we have a infinity over infinity type limit, allowing us to use Lhopitals rule. I want to go back over here. All right, let's go ahead and do the derivatives of the top and bottom. Using the chain rule, I do the derivative of this log first. The derivative of log of anything is 1 over that thing. And then we multiply by the derivative of the inside. Okay. Meanwhile, the derivative of cosecant is going to be negative cosecant of x minus 1 times cotangent of x minus 1. All right, so there we go. But honestly, it looks like we just made the limit much worse than it was before. Let's clean it up a bit. Maybe we can get something out of it. I'm going to move this negative out of the limit. So these will now be my denominator. And I'm going to move these to the numerator. And when I do so, they become their reciprocals. The reciprocal of cosecant is sine. And the reciprocal of cotangent is tangent. All right, now let's reevaluate this. If I plug in 1 down here, I have natural log of 1 is 0. And if I plug in 1 here, I have sine times tangent of 0, which are both 0. So once again, we're going to use Lhopitals rule, only this time we have a 0 over 0 limit. Okay, hopefully we're not using Lhopitals rule too much longer. This is getting kind of complicated. All right. The derivative of sine times tangent requires the product rule. So the derivative of sine is cosine. And then I leave the sine alone and do the derivative of tangent, which yields secant squared. All right, now on the bottom, I'm also going to use the product rule. The derivative of x is 1. And then I have ln of x. On the other hand, when I leave x alone to differentiate ln of x, I got 1 over x. All right, now we could definitely do some simplification here. Hopefully it'll be enough. We have negative the limit as x goes to 1 from the right. Now cosine times tangent is sine, because tangent is sine over cosine, so the cosines will cancel. Sine of x minus 1. And then I guess I'll just keep this here. All right. Now down here, what are we going to get out of this? So down here, we have ln of x from that, and then this is just 1. Okay, so now as we send x to 1, we have 0 and 0, so our top is 0. All right, looks like we're gonna have to use it again, but then finally on the bottom, we have ln of 1 is 0, and then we add 1. So this limit is 0 over 1, aka just 0. So you have e to the 0 or 1 as the result for this limit. All right, so there we go. That was a very bizarre limit, and that's probably on the upper end of difficulty of Lhopitals rule problems here. But the moral of the story is, if we have one of the 7 indeterminate forms, one of these 7 right here, and we need to do a limit, then we'll be able to use Lhopitals rule in some way. Maybe after a bit of algebra in these cases, or using e to the ln in these cases, we'll be able to use Lhopitals rule to help us out. All right, that's it for this video. In the next video, we'll learn how to graph different types of functions using calculus. I'll see you in that video.